to introduce my friend and colleague Muriel Medard, and for those of you who have been to the previous two workshops, you've heard the story, but it's I don't remember when it was, but right after graduating from MIT, Muriel was an assistant professor at the University of Illinois, and I was working on MDPs and queuing theory, and Muriel came in, and just it was an amazing time because it was Ralph Cotter was working in all this beautiful information theory work, and suddenly this incredible wealth of people in information theory, and I was there alone, playing with my MDPs, and it was Muriel who sort of dragged me out, and it got me into this area. So I didn't know much about, I loved information theory when I took it in college, but I didn't know much about it at all. So I can thank Muriel for getting me into the area, and so that's, I mean, so so I mentioned, Muriel's PhD was from MIT and in information theory under Gallagher, right? And she's has incredible service record and incredible contributions to information theory, as well as being an amazing mentor. I could go out and make a big list of the service, but in particular being president and vice president of the IEEE Information Theory Society. Yeah, never do justice. But anyway, we all know that her research in network coding and at various aspects of information theory and communication.
Well, thank you, Sean, and thank you for letting me be the co-organizer, where really you do almost all the work. So those are the best things in which to co-organize. Let me suggest that you co-organize things with Sean. And in terms of mentor, you were a fantastic mentor to me when I joined Illinois, because I don't know that it was so much I dragged you out of your office, but that you found me running around clueless in the corridors. And originally the title was Replacing Replication with Coding, and then it got slashed in somehow with coding ended up missing, and I realized it's actually a much better title. So both to make it look like we didn't make an error in the poster, and really because, by serendipity, it is really a better title. I'm putting replacing replication, which makes you think, with what? Ken suggested cloning. But I don't know how to do that. So all I know how to do, as already Sean sort of alluded to, is code. These are my collaborators. I have all kinds of wonderful collaborators. I should in particular point out to Frank Fitzek and also Amina Solianen, who works in the same group as Thierry. I'm going to do 3 case studies, and before you think, oh no, you're going to drag through 3 case studies, I'm keenly aware of the fact that this is the last talk, that your brains are fried, and that I should keep it light. But mostly I have to keep it light. It's not because I want to keep it light. It's because actually it is light. So we came up with a bunch of problems that I think are really good problems, in the sense that from an engineering perspective, they really have, I hope to convince you, interesting applications. But in all of these, it was always a little bit unsatisfying. In some cases, there'll be no analysis just because it's very new. We just did experiments. We're trying to figure out what's the right way to do the analysis. In others, there's little. And in others, we spent a lot of effort, but it wasn't very satisfying. So, but on the other hand, it was worthwhile looking at, just because the problem was interesting. You needed to get some sort of results. So my hope is, of course, that by the end of the session, you're still not so fried that you can't go, I know how to do it. I'd love that. Okay, so I'm going to start with the first of these, which is the advantage of recoding for survivability. So we're hearing about survivability, which is the reason I guess we're both in the same session. It's going to be a somewhat different survivability under dynamic conditions. Then I'm going to look at coding just for reducing blocking, and that's really sort of a big part of the replacing replication with coding. We'll see, why there is so much replication currently, particularly in storage area networks, and it's really not for survivability of the type that we think of, just being, say, disconnected or unable to retrieve something entirely. It's more for performance. And then I'll talk a little bit about scalable video coding, and in particular because I think that these issues of blocking really are very much at the core of why scalable video coding hasn't quite taken off in the way you would have expected it to, given the large amount of resources that was put into it from industry. Okay, so I'm going to give you examples. That's it. Just examples to think about what can be done. And here's my first example. And the motivating application here was that we have our phones and we have data on our phones, and we're going to be sharing it, and people are going to come in and out. Okay, so you've heard of the cloud, and many of you have heard of the fog, and that's not just how you would get up in the morning. It's also this idea that you have an ancillary network at the edge that you can use for augmenting your cloud network, where you have to get somewhere to the core. So this is a very simple, if you will, canonical example. I took a file, I made it into 16 chunks, and then I have a bunch of nodes, each of which is just holding 4 chunks each.
Disjoint.
Pardon?
Disjoint.
Yeah, these are so actually hold on to that, because I'm not going to tell you yet, but that's the right question. So I have 4 chunks, okay, and I'm going to be storing these in 10 data centers. I'm calling them data centers, which are in the cloud, but you could think of these as not necessarily being data centers, because the data center that only holds 4 chunks is not particularly interesting. But but again, this is just a small baby example just for us to think about. Okay, and then what we're going to be doing is we are going to, at each stage of operation, we're going to take 3 of the storage sites, or data centers, whatever you call them, at random, uniformly chosen, and we're going to just kill them. Okay, so I'm picking 3 at random, and we're going to say they leave. And so remember that I had basically 10 data centers, so I had 40 chunks to start out with. Right. And I want to come up with 16 chunks total, which is going to get back to your point. So it's not it's not unreasonable that I might be able to recover the 16 chunks from the remaining nodes. Okay? But of course, if they're disjoint, it's also not a given. And I'm going to be doing this at every round, and the question is, how reliably can the data be reconstructed?
Are you going to let us go?
How did you guess? That's because you saw the title before the second part.
Well, if you're going to let us code, then it's almost like you're telling us there's a man gets off the train with a bunch of bananas. How many oranges does he have at the end of the week?
That's right. That's right. That's right. So, yes, Ken gave it away. We're going to code, but before I code, because obviously if you just keep killing 3 at a time, eventually you would end up with none. So the guy gets onto the train with a bunch of bananas, and then you keep eating his bananas. How many fruit does he end up with? None. What I'm going to do is I'm going to have 3 storage sites are going to be coming in, and these storage sites are going to be connected to each other. Okay, again, with a simple random model, and these ones are going to have to be populated from whatever is around. So going back to this idea of the fog, okay, going back to this idea of the fog, is that you have, I mean, if the fog just dissipates, you can't use it, but you have other people coming into the room, say, and then you're going to be exchanging data, and they're going to become part of your fog. So people are leaving and coming randomly.
So the fog is the people in the room?
The fog is the people in the room,
Chris
right.
Is part of the fog?
Chris is definitely part of the fog.
Right, that makes sense.
Yeah. And so are you, Ken. Unless you just opt out. And so of course, this is very simple. You would imagine that actually in a better model, number of people would increase, number of people would decrease. There would be something much more interesting in terms of the connectivity. This is really simple. This is really dumb. So I started out with no, little, or unsatisfying results, and I intend to stick to that. Okay, so coding and recoding. So I am going to code, but I'm at least not just going to do only coding. I don't know why there's a 2 with a capital T-O, I'm sorry about that. So I'm going to use 2 approaches. One, which is random linear network coding. I'm not going to go into it, but basically just take whatever you have, you work over a large enough field, you mix it with uniformly chosen coefficients. And the other one is I'm going to use a Reed-Solomon code. And if you've seen, yes?
Sorry, you mean that each of the chunks in the 4 chunk things
will be one of these, exactly. Okay, so I start out by putting out a Reed-Solomon code, and so the thing that will happen with the coding and recoding is that, of course, if I have just chunks which are randomly mixed with each other, and then whatever's left over are randomly mixed, you know, the nice thing about having a uniform distribution and mixing with another, you know, again, is uniformly is that it remains uniform. The difficulty here with the Reed-Solomon, and this is something that, so incidentally, this is, as I said, a very, very simple model, but at least you can, this is the type of things that people are seeing already when they're having to regenerate inside storage area networks. We'll talk a little bit more about those later. Is that in order to have a structured code, you generally start out with your original data, construct a structured code version of the decoded version of the data, and that means that you have to go to what we're calling parents, basically. When I'm adding, oops, no, oh, don't give it away. There we go. When I'm adding, you know, this guy, these are the parents. This is basically what he needs, what he has access to in order to be able to get data. This new node that comes in.
So
yeah.
The new node has access only to whom they're connected.
Correct. So.
How are they connected?
Pardon?
And how are they connected?
So we're going to choose later. You can actually modify to how many people they're connected. But you choose that they're going to be connected, in this case, to 3, and you choose randomly to which 3 of the existing ones, of the surviving ones, you connect to.
Explain why you double code. That wasn't. So the next one you're saying you're doing.
So this is a good, yes, actually that I missed it. So the first time that I coded, I had my pristine chunks, I coded them and I distributed them. Now, after these 3 died off, right? After these 3 died off, the parts that are remaining were already coded, right? So if I want these elements on these nodes to be coded according to whatever structured code I had, in general, I will have to decode and re-encode. So suppose, you know, I mean, we take a Reed-Solomon code just because that's one of the most commonly used in storage, but, you know, if I take my data, I put it through a Vandermonde matrix, then, you know, I take out some pieces of the Vandermonde matrix, I may be able still to re-multiply it by a Vandermonde matrix, but what came out of that does not look like originally taking the data and putting it through a Vandermonde matrix once.
Is your point?
Yes?
the white box that comes in, if I just make it of the 3 other boxes using the same method I made to make the grey boxes to begin with, they will look different.
They will look different, and
They're all correlated as well.
yes, absolutely, yes. And that was actually, so keep that thought of the correlation, because that's actually one of the reasons we don't have anything interesting to say. So basically, with the way we're comparing, so looking at random linear network coding, each node recodes over the received packets, so just from its parents. Each of the nodes will store with high probability different coded versions, as long as my field is large enough, and that's, I get rid of the correlation that way. But it's not perfect, so you have every right to look doubtful and make a face. Each node has to retrieve, in this case for Reed-Solomon, enough segments from the remaining parents to decode, if possible. Then they store the information, and basically here, by the way, I need a little bit of overlay control entity so that the nodes are filled in correctly. So I need to make sure that whatever I got here would have corresponded to what it would have looked like if originally from these 16 chunks I would have made a Reed-Solomon distribution onto that network. Okay, so I want to make sure that, for instance, this one and another one, which maybe is not even connected, don't end up with the same pieces. right? So I'm providing the Reed-Solomon version, if you will, an extra layer of facility that normally I wouldn't have, which is to be able to tell what's on all of the nodes and do the best job, and I'm giving it that for free. Okay, so that I don't end up with completely identical coded pieces if I could have avoided it.
You're picking uniformly in a large field.
No. For the random linear network coding, I am. But for the Reed-Solomon, it's structured. Okay? So basically what happens is you have the ability to have a coded piece, and Anna has an ability to have a coded piece. I'm going to give it for free to you that you can make sure that you don't end up with the same coded piece.
Which would kind of suggest we could communicate in much space. Why am I restricting to 3 neighbors?
So I'm giving you for free the overlay. So you only have 3 neighbors from whom you can get the data, but I'm telling, because otherwise, so I'm giving the Reed-Solomon an advantage, which is that, you know, you can only, if you will, for free exchange with Anna to find out if you ended up with the same coded piece or not. If you could have avoided it. So it's basically, it's just a control entity to figure out, did you end up with the same coded piece or not? Right, but you're not exchanging data. Okay, so here's the results. And so here's no coding. There's the Reed-Solomon coding.
Yeah.
And right, and basically here are the axes. So this is the number of parents, right? How many you're connecting to. Do you remember in the picture I showed you there were 3, but you can vary them. This is the amount of storage per node. Right, so I showed you 4, but you could actually, of course, in the limit, if you can code, you know, keep the entire file.
What's the deletion fraction every time?
Yes, so actually, every time, in this case, I forget how many I'm taking out. I think in this case, I am taking out 4 every time out of 14.
Well, but that's wonderful, because eventually you do die. I mean,
eventually you do die, that's right.
I mean, yeah.
Yes, and I don't know when we die here.
Oh, that's so awesome. Wow.
Yeah,
How can you say it's not interesting?
Well, it's interesting in that it's motivating, but I don't have any results. I have a picture, I have a video for you.
Yeah.
It's embarrassing.
Well, there must be a Markov chain where you can get the second eigenvalue.
There has to be, but going back to what Ken has said, particularly with the Reed-Solomon, it's ugly as all heck, because, you know, I have to.
Oh, you forget that. But the
yeah.
coding, you can imagine there's enough structure you could actually get some.
Yeah, there's enough lack of structure, right?
Yeah, so let's kick the tires just a little bit. So
Okay.
you're starting, is this the exact same? You started out with your 16?
We all started out, yeah, exactly. Yep.
And then 16?
And this is probability of retrieval, and you can see as the number of rounds. So, you know, I go through many rounds of this, right? That's right, that's right. So we call this the melting ice cubes. It's kind of like this, you know, global warming looking thing. But you see that it is motivating. As I told you, I'm just going to give you a bunch of problems which are motivating in the sense that you go, well, I'd like to do this, but, you know, as a result, it's nowhere, right? And going back to the correlation that you were mentioning, Ken, keeping track of what's going on, particularly with this, you know, with the Reed-Solomon here, it's like, you know, you can do it by hand for like a few iterations, and then you look at the matrix, you have no, I mean, it just doesn't look like anything I've seen. So, right, so one approach might be to say, well, to heck with this, right? But this is important because, you know, this would be the kind of coding that you would use otherwise, right? And you can see that it's giving you a benefit over not coding, right?
But I thought you explained that was really hard to implement.
Yes, that's right. That's right. But you know, this is the standard right now. Okay, this is kind of the bread and butter of Reed. So, you know, if you were comparing it to any code, you would compare it to Reed-Solomon code most likely. So anyway, so I'm happy that Sean liked it, and yes, there must be a good problem there. It's hard, as you know, as Ken pointed out. I mean, what's happening from round to round to round is a pain. And, you know, so in this case, by the way, this remains stable. Even if we could say, you know, what's the region here? Because, so here's the probability of being able to retrieve, you know, that there's just enough, that the pieces over the entire network suffice to reconstruct the original file. right? So even if we were able to give some idea of what this border is here,
It just looks like you can artificially create a path that may have a tiny probability.
yes, exactly, yeah. So there's, yeah, exactly. So there should be, yeah, unless it's truly, yeah, exactly. Or you would have to figure out how much the, I think it's true. So I think that you're right. I think that.
It may not be true because there could be a probability 0. Like you may not be letting me delete enough when you move out there.
Yes.
That I might have probability 0 of eliminating the chunk.
It depends obviously on the number of chunks and number. Yes. So.
So when does it die, Muriel?
Pardon?
You yanked out, you have to have, somebody somewhere, you probably have to have yanked out enough chunks so that even the network coding dies. So when does the network coding die?
I don't know.
Well,
But it may not,
that's
though.
at the,
I mean, yeah.
well, no, if I knock out all 14 replicants or 10.
Yes. So yeah. So if I knock out enough.
There's a number.
So I need to have enough replicas. I mean, I need to have not replicas, but I need to have obviously enough nodes here. I mean, you know, if I have 16 chunks originally, then I can't go down to fewer than 4. Because, you know, you can't squeeze water out of a rock.
If you're doing 4 right now out of 10, have you tried 5 or 6?
So, yes, so we tried a whole bunch, right? And right now we did not see it die. But remember, the way that we're doing it, you know, is
So you can, so let's just play this out. Okay. You have 10 sites.
yes,
If you knock out 7 of them, clearly
we're done.
right, you're done.
Yes.
In simulations, if you take out 6 of them, so if there's only 4, it still does not die.
I don't see it die, no.
But no,
But it has to die at some point.
No,
If it's
no.
more, I just don't know. No, it doesn't have to die.
No,
See, I don't know. I've never seen it die.
You know, it wouldn't be, just think of
Sean's
grade.
on my
Like
side.
grade, no, but grade, just think of grade, the way grade works. I mean, you know, you could build grade drives and.
So the reason,
and this
No,
coding
it's a
might
matter
be-
of a number. What I just heard is that you go down to the hairy edge, you destroy everything.
Except for 4.
That's
eventually. You're right. So, but the point is, there are circumstances in which that probability should actually probably be 0. There is, I suspect, there is a phase transition.
Yeah.
And there won't be a phase transition for read home, but there will be one for the network coding.
Yeah. And that would be what that edge is. Because you can see here that, you know, if I don't have enough parents enough, right? So that's, and that would be what that edge, and that's what I'm saying. I think there's an edge here that we could characterize. I think this empirically, right? So it's not like no matter what, yeah.
It's just your question of Gaussian elimination on a number of equations. It's really a question of you've given me a big array of equations and you're going to delete a certain number of them, but you know you've got uniform coefficients.
Yes.
So,
over a large enough field, so
and
yes.
so if you only let me eliminate so many rows, what's the probability that the thing is not vertical?
Exactly. And think that you're working over the reals for all intents and purposes, because I don't care how big, yeah.
But surely that's the same as the original analysis for network coding. I would have thought that it's basically the same thing.
No, we didn't find it because, so we originally thought it would be, right? And in one shot, I mean, basically, so one shot, it's easy enough. You just say, look, the field is large enough that you can recover. But the difference here is that you're recovering the old ones from the new ones, and you have these parents.
Yeah, I still think as long as you prove something is probability 0, it's simple stuff. It won't matter. Because multiples of probability 0 is still 0.
Yeah, so we just couldn't.
Because if it's not probability 0, then Sean's original count is the Markov chain. And I should have an absorbing state means that everything would be true.
Would be, yeah.
So it has to be actually probability 0 if there's a phase transition.
So yeah, but so empirically that seems to be the case, but I don't know where the phase transition is. I don't know how to characterize it, which is why I was saying I think that characterizing this edge, which would be basically the whatever this is, this curve here, which would be the phase transition, that itself might be doable, right? But we haven't managed. This one is, this one I think we might actually, just like Sean said, just give up on. Even though from an engineering perspective, it's interesting. It's just horrible. I mean, I just don't see that we're going to get anywhere.
What's the
size of your resolving code? Is it dependent on how you choose your resolving code? Because
no. I mean, you can pick any code. I mean, any resolving code, and it becomes a mess after a few rounds. It's not
a linear network code. I mean, you can implement via resolving code up to the maximum size of the code, right? That you can just
no. But this is a random. This is a random code.
Yeah, but instead of doing random, you just have deterministic coefficients, right?
But remember, that has to remain a Reed-Solomon code.
Yeah.
Otherwise.
One last thing here.
But it's MDS code, so like you get any.
So you're right. They're all MD.
Then you decode, right, or whatever.
Yeah. No. Because remember the parents. That was the problem with the parents. Remember, I only have a. So the probability that I'm able to create a legitimate chunk of a Reed-Solomon from a subset of the parents, no, it's not at all given.
Right, well, I mean, you just have to have 16, like whatever. So if your redundancy is, if your initial number of chunks is 16 and you use your Reed-Solomon, right, then you just need to get any 16 copies.
On a one shot, but it's under the recoding that doesn't work. So you're right. After one shot, if it's a single shot, what you said is right. But when I recode under multiple shot, that's when it starts dying because I start having correlations.
Right. Well, that comes into the question about like how big is your code, right? Because then the bigger your code is, then the more coded versions you can create, right?
Yeah, but eventually it just dies off.
Well,
right, so it's going to be, so you can see that it maintains, this is the number of storage per node, which is actually the size of your code in effect. You can match it to that. Sorry.
I don't think you're quite answering Dan's question.
Okay, I'm probably not understanding it.
It's the same thing as you've allowed the network code field to be arbitrarily large.
Yes.
It's not saying, well, how big have you picked for the Reed-Solomon?
Oh, for the field or for the actual code?
Well, the code and the field are the same thing in practice, right? I mean, they don't have to be.
They don't have to be, yeah.
Shorten it, but why would you shorten it?
Yeah. Okay. Yeah. No, usually when you think you're like you look at your NK code, and I think your people.
N should always be, 1 minus the size of your field, or perhaps the size of your
No. Because here, no. Here, no. So usually when you talk about the size of a code, you're talking about your NK, right? Not the field size.
Well, but N is your field size if you singly extended code. Like everybody uses 256, right? Because it's convenient.
I see. Yeah. No. I see.
But the point is, you might get a phase transition in the Reed-Solomon
yes.
too if you have the field be big enough, which is what I think John was
I see.
saying.
So
the finite effect will be dependent on how many coded versions you could create, I suspect.
Yeah.
And that is determined by the size of your field.
So this is not. No. So I think. Yeah. No, you don't usually consider the Reed-Solomon code. I think you're saying go ahead and consider everything as an extension field. Is that what you're saying? But I don't know how to build arbitrary Reed-Solomon codes over arbitrary extension fields. There is
no, I'm just saying that, so I needed to do network coding for DARPA Spectrum Challenge. And rather than do random, or I wouldn't want to do random because I have to transmit the coefficients. I just did deterministic because I said I'm only going to send no more than 100-something copies. So instead of actually implementing linear network coding, I just grabbed the Reed-Solomon code. And did it
for a single shot, it will work, but for multiple shots, it doesn't. What I'm saying is you cannot take, if you're taking an n tuple, right, over whatever field size I'm using within that n tuple, right, that field size is still much smaller than if you consider that entire element, that entire packet as being over an extension field. You don't build the code over the extension field. That's not what you're doing in either of these. Right?
Well, we're not doing either of these. You did.
You did. Well, whatever you're doing, right? You're not using a code built over f sub, or f sub whatever q to the n, where n is the number of elements in your, right? You're reusing the header. You're reusing the coefficients over each of those n. It's not built over. So no, it's not. That's not the way it's built. It's not built over the extension field. You're not doing this. Pardon?
Oh, yeah.
Yeah. Yeah. So that's not a network, that's a one-shot code, right? And that's fine, but it doesn't work on the, so if you have a vector, right? And say I'm working over f sub q, and you're saying if I'm working over the extension field, I have n of them, and I'm working over f sub q to the n, that's not the way you're building your code. So even when we say that we're building it over an extension field, which we often do, in which case you almost always use binary, because why the heck would you use anything else, right? This is just replacing the q. You never do this, because then your coefficients would be massive. So it's not the same. The size of the code and the field size are absolutely not the same.
Well, I mean, read-solving code, the q is your n-1 if you do the, you know, the...
Yeah, but you can't do that over an entire packet. You're not coding, you're not considering the entire packet as being an element in your field.
No, you're not,
okay.
No, you're streaming down by queues. So
exactly,
queues
exactly.
Right?
So the aspect is we haven't found, you know, we tried in several, and we have not found a single, we have not found instances where the read-Solomon code remained stable because of the structure.
How sensitive is the size of that? Because
that's a good question. So I don't know how sensitive it is.
Right.
Everything that we tried to eventually, because you will not be able to maintain the structure. But I just wanted to make sure, this is not what you do over a packet. You're not using. It's not okay.
If it does, but I thought that would answer John's question. If you made your little blocks massive.
Well,
yeah, but there's massive and there's massive.
Yeah.
Okay, so basically, like the chunks of megabytes, you're not using a field size that would be. Sorry, you were. Yeah.
It's still a math question, right?
Yes, it is.
You can't answer a math question with a practical question.
Oh, okay, yes. No, but I was just wondering. No, when he was saying that he used a structured code and it's a.
Make it big enough, would it also stop falling away?
I don't know.
But your only answer is that you tried several.
Yeah, so we tried to, again, remember, I don't even know what's happening here, and this one's easier than that. So,
yeah, I was just wondering whether how, if the rate at which we're seeing is depending, because if you take, say I'm coding 16 chunks together, and so maybe I pick a 6416 extended read-Solomon code to implement it. Then the number of equations I can create is 64. You know,
that's
I've chosen this read-Solomon code. But if I choose a 25616 code, I can create 256
absolutely,
equations.
yeah, absolutely.
It presumes that curve would stay robust for longer. And not
I see. So I would assume that it does too. Yes, it does. So the answer is it does.
But
yeah.
Also, the reason why you're getting a plateau on this other one is because of the number of equations that you can create, and so the probability that you have to have the equations are the same. So that's why.
Yes, absolutely. Yes. So I see. Yeah. So the field size is not the same as the size of the code in terms of kn. All right. So from that perspective, and you're right that both of them are MDS codes. So yes, you will remain steady for longer, but eventually you will die. I don't understand enough of either of them, frankly, to tell you how much more slowly it will die. Right? Because remember, this one is the easiest, and I still don't even understand why this one doesn't die. Yeah.
It's not, you don't know that the other one wouldn't die.
I haven't seen it not die. Correct.
So that's different.
Yeah. I don't even know how to make that one not die. Yeah.
But it could just.
Yeah.
Okay. I think John's conjecture, which I don't
is
know
that
is basically that.
There might be.
Increase it, eventually it gets to a limit that looks like the network coding where it won't die.
And that is the.
Essentially, for any practical system, you have a finite block size, and then the amount of network coding you can do, you run out because you just have a certain block size, right?
No, because you re-encode. You don't keep you don't.
Oh, I understand that, but so we're choosing my coefficients from GF2 to the whatever.
It's still discretized, right?
And
pardon?
It's still discretized. I mean, you're still,
you're
not using coefficients, right? You're using something in a field, right?
Yes, that's right. I'm using in a finite field. It is discretized, yes, yes.
But if you're working, say
so eventually, yes, it should.
Over GF2 to the M.
Yeah.
Well, my GF2 to the M, eventually, I can only make so many.
Correct. In which case that should eventually die. Right? Because there's always a non-zero probability, going back to what Ken said, that eventually, for instance, even I just end up choosing all zeros on all of them.
Yeah, but in the limit, as that field becomes arbitrarily large,
that becomes small.
It actually phase transition to a being 0, but you might expect the same thing to happen in the Reed Solomon if you gave it no advantage.
Yeah, so the problem with the Reed Solomon, frankly, I don't think it's so much the field size. But so let me tell you why I don't think it's. So the first answer is I don't know, but I don't think so. And the reason is because the thing that kicks me in there is the probability of being able to keep the structure of Vandermonde matrix. That what's left over allows me to maintain the structure of the Vandermonde matrix. That's what's getting me quickly here, relatively quickly. So if I go up in field size, it does help, right? Because the thing's just more robust. But the problem is that in order for this to remain looking like a Reed Solomon code, it needs to still, it doesn't just need to keep the same field size, it needs to be able to maintain the structure. And what happens here, from what we've seen, but again, you know, not proven, is that eventually you cannot maintain that Vandermonde structure. It just does not look like a Vandermonde matrix. The pieces that came out are such that, given the parents to which you're connecting, you cannot recreate a piece that looks like it would have been from a Vandermonde matrix. Does that make sense?
Yeah, I mean, I understand. I'm just curious.
So you have more choices. You have more choices, but you have to look at that structure, and that's what. Again, that's what it's getting us here. So I suspect that not, because the thing that kicks in is this. See, here the thing that would kick in is that I end up just, you know, taking lousy coefficients, right? Here the thing that kicks in is, given the number of parents I'm connecting to, I just cannot create something that overall looks like it would have been from the beginning. The parents that I'm connecting to are not going to allowing me to make that part look like I had originally come as a.
You can't decode, because if you could recover the information, then you could.
If you could decode everything, right? But it's like even if you couldn't decode, I don't have a means of reconstructing something that looks like it came out of a Vandermonde matrix.
We're holding you from miles to a lot.
Oh no, but this is good. I mean, you know, the other stuff is of the same ilk.
But like say the access here, so I could have connected to all the parents.
Yes.
And if I do no coding, I'll still end up in trouble. But if I connect, if everybody connecting to all of the parents, maybe the Reed Solomon.
Yes, the Reed Solomon. That's right. So the number of parents was such that it never exactly. So in that case, I could decode at every time, and I could re-encode. In that case, yes, absolutely, it's stable. Okay. Which is actually why we never show the 14 line, because that one's trivial.
Presumably it still dies out for the no coding.
For the no coding, no. If you always have, let me think. Yeah, I guess for the no coding it would die. Yeah. But we didn't show the 14 line just because it was not interesting, right? But yes. So in the Reed Solomon, if I could decode it every time, but then basically it's like I'm back at round 1 at every time. Right, I just start out by placing everything out, right? But it's not the field size that gets me. It's the Vandermonde matrix, I think, you know. But all right, this was good. So you can see why it's interesting, and you can see why it's non-trivial. And some more things where we got nowhere. Recoding to reduce blocking. So this is a little bit more, so by the way, here where you can see why the title, you know, I am trying to reduce, you know, I get a better benefit by coding than I would by just having more replication, more storage, right? So coding is doing better than replacing storage in this case, because, you know, the replication actually wouldn't get me anywhere, or would only get me so far. So no, this is good. All right, so, coding to reduce blocking. So coding to reduce blocking, so very, you know, people often when they give talks on storage and coding, they say, oh, you know, if you look at Facebook, you know, they keep like 18 copies, and obviously they would be better off doing storage. I mean, doing coding. I mean, who uses a replication code anyway, right? And the answer to that is, well, you're right, that would be silly, but that's really not the main reason why people use coding. And I'll show you 2 examples, right? The reason people use coding in storage networks is for availability, for accessibility, right? So that you're able to get the data quickly, not because you're afraid that you've lost every single copy of that person's Facebook page. You don't need that many copies, right? Too many things might be wrong. And besides, you know, often you will keep several copies in the same data center in different disks, right? So, you know, if you were really worried about that data center going down, why would you keep it all together? Okay, so here's one example. And this, again, we implemented, and then we're trying to figure out what's the right way to analyze it. So you have a coded cloud, and what you're going to do is you're going to put random linear network coded chunks in each of these servers, and of course the nice security aspects to this that Ken and I are trying to look at. Pardon?
I'd love to see the...
Yeah, because each random code. And by the way, there you're really happy that you don't have a systematic code because that takes you somewhere else. So here are a bunch of them, and in order for you to download, now it's not necessarily that you've split it up. Okay, so it's not that you put 1/4, 1/4, 1/4. You may be putting more of your file on each of those. At the maximum, you would keep, say, a copy of your file on each of these. Okay, that would be the maximum that you would keep as a full copy. And here's an example of just one run, and here is an experimental some experimental results on the right. So I'm not going to tell you which of those clouds does better out of the 4 that I showed you. And the funny thing is, they swap around who's better. I mean, literally, you'll just be there, and in the morning, one does much better. In the afternoon, another one does better. Pardon? So better, so I'll tell you in a second, okay, how they're working. But so here is the chunks that I'm getting, the time for me to be getting from these different clouds. And here's the first time that I got it, right? So some clouds take a long time to even respond, and then give you something every so often, so this is not a very good cloud. This one starts quickly and sends you a whole bunch of them. This one starts quickly, but then it's kind of slow, right? And this one started slowly, but in the end, I got more out of this one than I did out of that one. Okay, and the time here, the magical time, is when I was able to decode. I got enough coded chunks that I was able to shout bingo and be able to decode using Gaussian elimination. All right? Yes, Thierry?
What about the different clouds in their structure? Are they comparable, or?
I don't know that much actually about how they work because they don't tell us, and we're just using them in a dumb fashion. But it was surprising how inconsistent it was. Yes.
I don't know where you do it from.
So.
From your office.
So I'm sure it depends on where it was done from. Most of these were done in Denmark and in Germany, so in Aalborg and in Berlin. Pretty much from the same offices, just at different times, and even there it was very different. I'm sure it depends madly on where you are also. What was surprising to us is how much it changed even when you weren't moving around. And it changed pretty quickly. So if you look at some, I thought of putting some slides on that, but it's just, So if you look at some of the scheduling algorithms for peer-to-peer, which goes back to the question I was asking Anna this morning, generally they do this estimation of the available bandwidth, and then they schedule according to the available bandwidth, right? And here what it looked like was that even that estimation of the bandwidth over the period of time required to download a file was not that great, or maybe, it's, yeah. And so there are different problems here, and just in terms of, again, going into, why do we not even have, I would say, a pretty formulation? So if I have only 2 clouds, right, and I don't code, right, because I need to compare this to an uncoded system. It's kind of simple what you would do. You would start from the beginning of the file on one cloud, from the end of the file on the other cloud, and eventually the twain shall meet. If I have 3 clouds, then if I don't have an estimation, it becomes a little harder, right? Because I could start at one end, the other end, and of course you have one in the middle, but you're not quite sure the one in the middle how much it should be going to one direction or the other. When I have 4 clouds, it becomes, I don't even know what the optimal approach to this is. And when you have 5 clouds, so basically what we did is we did a heuristic where we just, split it up into 5 using the kinds of estimates that people do now for estimating bandwidth, and did it that way. Okay, so here's the time taken. This is the number of packets available on each cloud. So originally this one had 32 packets. Okay, so this is the case where I kept everything on every cloud. Okay, and of course, if I keep fewer than that, then I don't even have enough things. So 7 because it's 7 times 5. So, if I went to 6, then it would only be 30, and that would not be enough. Okay. So anyway, here you can see. Obviously, I get a better recovery in terms of average, in terms of also variability around what I can expect. It's much better. So going back to something that looks promising, it looks promising, right? It's definitely worth looking at. We don't have anything clean to say. And the reasons are many. First of all, I'm not even quite sure what I really should be doing on the uncoded side.
But like you say, you don't know what to say because your baseline metric is difficult to define.
So the baseline metrics is itself difficult to define.
Anything you do is
yeah, I'm not. These things don't look. After doing some of these, I'm sorely convinced that these estimation approaches. I mean, okay, so there is option B always, which is just wimp out. I'll show you another time when we just wimp out, right? Which is just say, okay, look, this is the way people are doing it now. These are the estimates that they're using, or I just come up with some goofy statistics for how these work as to when they start and how quickly they distribute, right? So we can,
But you're using network coding on the left, right?
here I'm just showing you, when network coding finishes. In network coding, I don't need to know the different speeds.
Right, so you can probably prove that that's better than.
So proving that that's better, yeah, that much I can.
That's all you need to do.
Yeah, but you'd like to know by how much, right? Because I mean, you can show that you can show that it's better, but yeah, the difference matters, So, yes.
The question is, for this figure,
yes.
we have the 4 streams.
Mm-hmm.
When you do decoding, you use all the packets you receive from the different
Yes.
streams. Oh, I see.
That's right. So once I have enough packets, like I said, I just shout bingo, I had enough packets, and I'm done. Right.
From the 4 different streams.
Correct. So I'm just pulling from the 4 streams as fast as they come, right? But you see that if the packets, because the packets are coded, here they're interchangeable. If they were not interchangeable, then it would matter because, I have to then schedule, and it could be that I thought that because this one started quickly, that this was a good bet, and I could be scheduling to get some of these, and then, I'd have to wait for those. So that's why, we did some heuristics which were, frankly, somewhat better than what we were finding in the literature, and then we just tried it out. Does that answer your question?
Yeah.
Yeah.
I thought you want to compare the performance of different clouds.
No, the clouds are what they are. No, I'm not trying to compare the performance to different clouds. Sorry for being unclear. Not at all. No, these are just...
The idea is no matter what the order of the clouds is, who cares?
Exactly.
You always do as
Exactly, yes. That's right. I always do as well as I can. So from that point of view, I can prove that. But, the question is, how much better off am I? Because, if it's very little, then maybe it's not worth it. So another example here, so kind of a motivating problem, and actually this is working better than I thought because I'm getting far more questions. So now I'm wondering, maybe I won't talk about multi-resolution. I'll just talk a little bit about storage area networks, as I promised. And this one we did a little bit more, but as you'll see in the end, it's also it's kind of unsatisfying. So storage area networks. So storage area networks are dedicated data storage networks, of the kinds that you would find in sort of large data centers. So they're quite architected, quite controlled. And the way these things work is generally, there's more and more, variability. There's more choice right now in the types of storage medium, but by and large, it's still disks. Okay, it's really hard to compete against disks price-wise, and basically, you will have the way that it's set up on this the different disks, which we're denoting by D, is you'll have different pieces of a file. Okay. So for instance, here I'll have these pieces, file 1, 2, 3, and the reason, by the way, it would be laid out this way generally is you have something called striping. So striping is basically that you're pulling simultaneously from several disks. So you wouldn't put piece of file, this is I, piece 1, 2, 3, because I read it on that disk. I'm actually reading these and these and these. Okay, so that's how the striping works. And you have different issues in storage area networks. You have the drives, but then you have the servers to access those drives. And believe it or not, a lot of the cost in these is just coming from the controllers for the servers. Okay, so if you think that load balancing is kind of not that interesting, the cost of the load balancing hardware in these things is huge. And doesn't tend to come down that much. So actually that's part of where the big bucks are there. Blocking probability. So the file is blocked. I cannot get a file. It's one or more of its chunks cannot be accessed. It should be owing to rather than due to. Unavailable input-output access bandwidth drive slots, which can happen either because I cannot access on the server side or I cannot access on the drives. Okay? Now, generally what happens then is that you will have a certain number of copies stored. And the other thing to think about when you're looking at these disks is imagine if you went to a library, right? So you have several copies of a book, of the more popular books. The reason is not because they're really afraid that somebody will never bring back a particular book and they can never buy it and replace it, right? It's because it's more likely that that book has been checked out. Now imagine that what you have with a drive is that when you check out a book from the library, rather than just checking out that book, you check out the entire shelf that had that book, that entire disk, right? So then you would end up keeping more copies, right? And you would make sure that you don't arrange them alphabetically. You would actually arrange them for sure in different shelves. So that's basically what's going on here. So why does the coding help? And by the way, it will show up that it wasn't that obvious to us that it would. I'm showing you the reason why it helps. You'll see in a minute that there's a countervailing reason. So in an uncoded storage, let's just say I have, you know, file I, chunk 1 and chunk 2. Let me just look at chunk 1 and chunk 2. And you have a request for chunk 1, and you get it. You request for chunk 1 somewhere else. It's not available while you're reading that one. Okay. Then you get the request for chunk 2, you're fine, but if another one comes at the same time, you have a problem. Okay. Now, for the network coded, I'm requesting a degree of freedom, that's to say an equation that includes chunk 1. Okay, so you get either of these will do. So your load balancing, your upfront load balancer has an easier job. And the next one comes in, and you can see that you're not blocked. Okay? And so the same picture as on the left in terms of the sequence of requests, but you're making your requests a little differently. Okay? So the blocking probability here, as I said, file is blocked if one of more chunks cannot be accessed. So here I got 2 blockings there, it never did block. Okay. Oh, actually, it suffices for there to be a single blocking. Okay, so you have a lower blocking probability, so normally that would mean that since you're keeping a lot of files, not for redundancy in the case of, you know, disaster, but really for accessibility, for availability of not blocking, you should be able to get away with fewer drivers and servers. Yes? Yes, of course.
Yeah, it's like you're getting half the bandwidth, but you have the throughput. You have to have only 2 requests there.
You had 4 requests here. 2 people. So one person came and asked for piece 1 of chunk 1 of file I, and then another person did while that one was busy.
Oh, so it'll still be the same. Okay.
Correct.
It'll still be 4.
Yes, exactly. Yes. And so basically, you had 2 people that started watching a movie, one soon after the other, while you were still.
It makes sense if you think of the 2.
Correct. Yes. Otherwise, it doesn't. No, that's a good question. That's right. Yep.
How to calculate the coefficient A1 and
Oh yes, I'm sorry. That's a good point. I neglected these. These are these coefficients chosen over a large field size, chosen uniformly over the field. Okay. So it's as dumb as it sounds. All right. Yeah. So, okay, so first place where this is really not satisfying. And we're invoking the Kleinrock assumption. We're waving our hands. I liked your hand waving. And actually, this gets back. I think you were waving your hands, and then Ken said, maybe you don't need to wave your hands. Maybe you can do some. But here, actually, I'm really waving my hands because I think in your case, like, you could actually come up with a real. I don't think this is true. All right. That read requests for each chunk are Poisson distributed, independent of other chunk arrivals. There's no reason for us to believe that these things are Poisson distributed. And the other thing is, I really don't think they're independent chunk to chunk, because generally you will start reading and you will read all the elements in that chunk. So if anything, they're clumped, right? So the only thing that I can say here is maybe there are enough people watching the same movie at the same time, going back to your question, Sean, you know, sort of that you know, the request for the second chunk is not related to the request for the first chunk. It's just coming from somebody else. Okay, but that is so unsatisfying. You know, I make no bones about it. And yeah. Anyway, but you know, you would really need a model for how many people are accessing the storage and so on in order to do something better. So what we're doing then is just going to have a bunch of different IID processes, one for each chunk that you might want to get. And remember that we're keeping W copies. Okay, we're striping just like I showed before. Okay, so this and you know, basically we're assuming, because of these assumptions, which are we admittedly highly dubious, we assume that we have S independent NGKKQs. And here's in the uncoded case, okay? And there, again, if you're willing to give me this, and basically I can find the probability of blocking. That's to say that at least one of these is blocked using this analysis, which, you know, I'm really not happy about that. I'm really not happy about it, but I don't know what to do about it. Okay. Now what happens if I code? So at first, you remember the little example that I gave you made it look like, of course you're going to do better. But it's actually a little bit more subtle than that, because it looks like I'm going to be doing better. By the way, here I'm going to assume that my generation length, which is how many packets I'm combining together, is going to be half of my striping number. It's just an assumption. It turns out to work well, but you know, I don't know what the magic number is. By the way, the trend in industry has been for striping numbers to go up, as you can imagine, right? You're parallelizing more and more and more. All right? So you have a pooling effect provided by the network coding, right? I don't just need to grab, like I did here, a particular chunk. I can go ahead and grab, you know, basically these different coded pieces. So I have that pooling effect. That's, you know, how I'm keeping these coded pieces. But now, and it's still going to be MJKK but now I have fewer Qs. So the pooling effect seemed like it would be good, but the fact that I have fewer Qs to play with is generally not helping me. So it wasn't entirely obvious to us, actually, when we started out, which of the two effects would win.
What is your measure for winning?
So the measure for winning is my blocking probability. I'm only looking at blocking probability, correct. All right, so lowering my blocking probability. So the pooling effect is going to increase the number of available service units, but it's decreasing the number of total queues. The first one is positive. The second one is negative in terms of, yeah.
Are the lengths of the pooled queues longer then? So, because you.
Yes, yes, of course, because I'm pooling, yes. So so
that's a bit more apart.
Yeah, so it eventually worked out, but it wasn't totally obvious. Wait, okay, so it's obvious to you right away. It wasn't obvious to us right away. All right, so anyway, so we went through, we chugged it. It was just, but you know, the whole time you're going, I'm really not happy about that first M, but okay, let's just do what we can. And let me just skip to this. So this is uncoded. U is uncoded storage, and then C is network coded storage. And this is the this is with striping number. Okay, so you can see the probability of blocking. This is how much how much storage I'm giving, how much, and uncoded versus network coded. You can see the network coding benefits from having, you know, so here it was at striping of 2, here's at striping of 4. So, you know, the blocking probably scales well with striping number. Typically, for many of these systems, you want to be somewhere around here, very, very low, within a data center. It's not the end of the world, by the way, if you get blocked within a data center, but you have to be sent to another data center, and that's kind of a pain. But it's not, you know, it's not horrible. Anyway, so that was to give you an idea of the kind of analysis that we can do. I'm not going to go through the multi-resolution. Yes?
I just want to see the...
Yes.
Okay, thanks.
Yeah, and so, you know, I mean, I have to tell you, this is not... It's just, you know, you find these two formulas. Really, mechanically, it's not. But I'm really not happy about that initial model, and I'm not quite sure, and I haven't found anything. And the only things that I have found, frankly, are through consulting. I have found things that are traces that are proprietary. But I haven't even found within those proprietary traces anything where, you know, people have looked at enough traces to even come up with reasonable statistics that then you could share more widely, right? So, so this is, you know, this is enough to make you think that it's believable, but it's not clear from that it's, you know, what exactly would happen if my model was better. So that's it. I'm just going to stop there. All right. And thank you for being so interactive. Yes. Thanks. Are there other questions?
I mean, if I put network coding on my salad, does it taste better?
We can try. We can try. I'll buy you a salad and you can do it.
You know, cute, but it's beginning to feel like an organizing principle.
Well, I'm running around. I have a hammer. I run around looking for nails, to be fair. But then, and then I look at
all the time. I mean, everybody does that, but it doesn't always work. So are there places where network coding sucks?
But is it not the case that the reason why it works is it's always a relaxation?
Yes, it's exactly it. That's exactly it. You're relaxing. Yeah.
It's always a relaxation.
Yes. Yes. So, for instance, when you're doing multicast, it's a relaxation. So, you know, you look at Steiner tree packing. That's hard. What the network coding gives you is that it relaxes the integer constraints in the Steiner tree package, so now it becomes a linear program. And
so like if it always contains a special case of the original problem,
yes,
really do any worse.
That's right. Which is why it's more on proof. Which is why I love it. Yeah. No, it's.
I mean,
yeah.
I'm going back to the biology. I mean, there's a lot of things. You think of DNA as a linear code, but it ain't. It's chopped up. You know, things are mixed and mashed all over the place, and that's kind of what you're doing. You're just doing it in a very structured sort of way. So I'm just wondering whether it's an organizing principle when you want to preserve something. I
don't know.
Yeah, I'm kind of. You know,
you're looking at, yeah, you know, remember, I'm hanging out with discs, you know. They're dead, they're not exactly mysteries of life here, you know, like striping, you know. So, pardon?
No, we'll be striping mice.
Striping mice, that's right. You had a question, yes?
Yeah, so regarding the scalable video coding,
yes.
do you have anything to say about this?
I do, but I don't want to bore you because, you know, my time's up. I mean, I'll just say it at a high level. So if you look at scalable, so scalable video coding is generally built on multi-resolution code. So you have a layer 1, and then if you have a better rate, you have a layer 2, which works with the layer 1, and so on and so forth. And to make that, to make it to be scalable, multi-resolution versus just having one version that works well if you have this bandwidth and one version that works well if you have the other bandwidth, usually three different layers, you lose about 20%. That's the order of that, you know, order of magnitude of how much you sacrifice in efficiency. 20% of the bandwidth goes into that. And so, as you know, H.264 was scalable video coding, and people put a lot of effort into it, and particularly into making it parallelizable. Okay, so you know, TI put a huge amount of effort into H.264, and H.265 is starting out now, and you know, you see that many companies just gave up at H265. They said, you know, people haven't been really using our chips. They're not willing to pay the extra for scalable video. Something must be wrong, right? And if you look at how things are stored, or how data is called right now, and this gets back actually to the issue of measuring bandwidth, is that you have a lot of companies, you know, actually a lot of them out of CMU, that do available bit rate measurement. And then the way the video is stored is not in layers. You're basically storing it layer 1, or layer 1, layer 2, or layer 1, layer 2, layer 3, separate. You're not coding per layer. Okay? So that means that when so suppose you're my CDN, right? And in between I have my available bitrate measurement company, Sean, who's making money hand over fist starting this ABR company. And you know, my bandwidth goes down. He goes, oh, never mind, Muriel. I'm going to take you to a lower resolution. What happens is now that, you know, I was pulling from you, say, layer 1 and layer 2, and now I'm only pulling layer 1. I was pulling a copy that you kept, which was layer 1 and layer 2, and now you send me to another copy, which is being kept by Thierry, which is just layer 1. Okay, so at that point, first of all, why was there any reason for keeping your copy as a layer 1, layer 2, given that that's in general a more inefficient representation coding-wise? That if I had just said for whatever rate is, you know, for that particular rate, you can only get, you know, medium resolution. So, so now suppose that I also allow, so suppose that first of all I have to allow you to keep the layers separately, and now suppose that on top of that I allow you to code among the layers. So Thierry's keeping layer 1, you're keeping layer 2, and Anna next to you is keeping a combination of the 2 layers. Right? Now, when my bandwidth is good, I can either get you and Thierry, or I can get you and Anna, or I can get Anna and Thierry. Right? Which is already better than if I could only get you and Thierry. Now my resolution goes down, now my bandwidth goes down, again, depending on the availability, I'm back now just to having to ask Thierry, which was no worse than before. So the benefit, the likelihood, if you look at the likelihood that you'll be able to accommodate higher resolution, it will actually increase if I allow coding across layers in the storage for the same level of storage. And then we did come up with Markov chains. And I was gonna, you know, I was mostly hiding my shame because we came up with this Markov chain that looked like, you know, it should be solvable. And we found some things in the literature that looked like they could solve it, and then it wasn't quite right, and we gave up, we wimped out, and we just did Monte Carlo. And I'm not proud of it, but really, it was just, you know, and again, it goes back to the problem, you have a problem which is motivating, you come up with kind of a lousy model, and then the lousy model is not in itself even elegant, and, you know, it goes to the unsatisfying. Which was why I started with no, then showed you little, and then went to unsatisfying. This was actually, you know, so you missed the unsatisfying.
No, we didn't miss it. Even more unsatisfying.
Pardon? That's right, that's right. It was even more, trust me, you know, you don't want to see, okay, yeah. I don't know if that answered your question or not. That's right. That's right. Thierry, yes?
What you just said about the scalable video, is there a connection between that and the TCP stuff that we've done with images?
No, 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 that was purely...
It sounded a little bit similar in terms of, I don't know, you just said something that triggered me to think that there might be some...
There might be a connection which I'm missing, and heaven knows that that's quite likely, that if there's a connection, I'm missing it. But I don't know what it is. In that case, there was no scalable.
If your channel quality changes, then you trigger retransmissions, but you can maybe...
So actually, yeah, in this case, there's no retransmissions.
No, but it sounds a bit like channel quality changes, you have the retransmissions, but that's somewhat similar to your bandwidth is different, you go to a lower...
So actually, in this case, it's not so much that you're sending stuff that you could have avoided sending with this ABR. What happens is that if you will, I completely negated the benefit of having SVC, because it's not that Albert kept sending it to me and I simply said, oh, you know, you wanted to send it to me at bandwidth B, but instead I got it at B over 2, not quite B over 2, and I only got the low resolution. We're actually switching entirely. So it's not a question of retransmission. It's just a question of the fact that if I was only going to access you when I had enough bandwidth, why the heck are you even keeping it in a multi-resolution manner? You shouldn't have. Right. And actually, I was talking to Vivienne Shea, who did the design for the H.264 TI chips. She managed to do the parallelization, which is a huge deal in these things. And I was asking her if she thought this was the reason why it hasn't taken off, is because of the way it's stored, and the way it's stored is because of all this ABR stuff that's come out, right? And we talked about it for a while, and she goes, oh, I think that's why. I was wondering, she's like, my algorithm is lovely. It's like, no, your algorithm is, a piece of beauty. But so I haven't seen described, but I think, it makes sense, right? If you have all these ABR companies and so spent a fair amount of time also talking to the guys at NBC Universal, and one of our sponsors, and they say, oh yeah, no, we only use, they have a set of, like I said, almost all coming out of CMU, these ABR companies, and so that, that kind of explains why, if you're going to do it this way, then why would you store it, and why would anybody pay for it, versus just having different coded versions, which seems to be the way the industry is going. But maybe it would be different if you were allowing coding between the layers. All right. Any other questions? Should we be saying thank you?
Yeah, well, first of all,
thank you, yeah. All right. All right, and
I guess, yeah, so we can